Okay, the plan for today is to finish up chapter 6, talking about 6.5 on polynomial equations, and then start into chapter 7 on rational expressions. So chapter 7, I think, will be probably starting to move into territory that you may not have seen in the past, depending on how extensive your math background was. But I know a lot of stuff up to this point was review. But I think chapter 7, if you have seen it in the past, even it does take a step up in difficulty. It starts using several of the things that we talked about throughout the course. So, if you feel like it's been a pretty smooth ride to this point, I would, plan to dial it up just a little bit in chapter 7. So maybe taking a little bit more care to do things like read ahead or to work some extra practice problems in the book, um, before attempting the homework, things like that. So we will start in chapter 7 today. And just a quick announcement, Unit 2 exam is this coming week. I'll, remind you next week as well. Just make sure that you have done the Examity stuff. Have done the Examity practice exam, logged onto Examity from Blackboard, created an account, all of that kind of stuff, just to make sure that all the tech is working properly. One minor note, I have a class that took an exam last week, a fully online class, and some of the students, for some reason, um, when they went into WebAssign and clicked on the exam just so for the actual midterm exam, for them it was a midterm exam, not a unit exam. Um, the exam just opened up. It didn't go to the password screen first, and I don't know why that is. I think I have a suspicion why. So I actually have a class of students in a different course that's has an exam this week, who I'm going to kind of check how that worked with them. Um, but long story short, this coming Monday at 9 a.m., you'll see the Unit 2 exam visible on WebAssign, but please try not to click on it. Try not to click on it or start it. And when you do, until you intend to start it. And when you do intend to start it, please make sure to go through the whole Examity stuff first and get the session up and running before clicking on the exam. It's not the end of the world if you get that out of order or something, or if it kind of starts up and then you start the Examity session. It's not that big of a deal. Just, keep going with the exam. But but I don't want you to click on the exam and have it open up and then have the timer start and then try to do the Examity stuff. So I don't want you losing time while you're getting the Examity session set up. The material will be chapters 4 through 6. I'll have a sample exam posted probably tomorrow. It'd be nice if I could get it up today, but I'll try to get it up today, but it's more than likely going to be early tomorrow. So sample exam posted, and you can use a calculator, scratch paper, and pen or pencil. Same as the Unit 1 exam, no books or notes, and no phones or tablets as calculators. Okay. And the quote of the day
Can I ask you a
today is
question real quick?
by, oh, is there a question?
Yeah, I was trying to do the Examiny practice on WebExam, but it said I had to put a password in. Do you know what that is?
The Examity practice exam, you mean?
Yeah.
Yeah, so I would recommend, I posted an announcement about the Examity practice exam, uh, and there's a user guide that's linked there, and there's a video that's linked there. I'm going to post actually more detailed instructions about Examity. A lot of people have been having questions about it. Um, but if you look at the announcement and uh, those two resources, they kind of explain the whole password situation. So Examity will put the password in for you for the Examity practice exam.
Okay.
Yeah.
Thank you.
Yeah, so basically that password is just there to make sure that the Examity session is up and running and started and everything is working well on the Examity side before you start the exam.
Okay.
Yeah. And that screen is also the screen that was somewhat troublesome in the midterm exam on my exams in my class from last week, and I'm hoping that I've got it fixed for the class for this week. So we've never had trouble with it before, but for some reason, um, the class last week, and I mean, it wasn't anything the students were doing. Like, I looked at their video recordings and stuff, and it just let them right in for some reason. I don't know if it was a WebAssign glitch or what, but
I have
yeah,
a question too.
sure.
It tells me that my device is unsupported. I have an iPad. So do you need a laptop or you can't use the iPads to take the exam?
Yeah, you would probably need a laptop. You can always, send me an email or pop in office hours, and we can take a look at it more specifically. But it's probably, I would guess you need a laptop. I'm not sure. Yeah, we can definitely take a look at it though.
Okay.
Yeah. Okay, so let's jump into it. The quote of the day today is by financial guru, I guess you could call him Dave Ramsey. And one of his quotes is desperation precedes stupidity. And, I know that this is absolutely true for my life, that whenever I let myself like come right up on a deadline or something and I'm very desperate to get something done or very desperate to, make something work out, I tend to make worse decisions, you know, decisions that maybe more benefit me in the short term at the expense of long term or things like that. Maybe decisions that aren't best for me. So when you can, it's not always possible, but trying to avoid being put in the position where you're desperate, right? Maybe that means planning to take the exam next week, say Thursday night or earlier. So that way, if anything goes wrong, you have plenty of buffer, right? It's not a desperate situation. If you plan to take it Sunday night at 7 p.m. or something, and then something goes wrong, it's like, well, there's a lot fewer resources, a lot fewer options available. So just a short idea or quote today, but that's our quote of the day for today. Okay, so moving on to polynomial equations. Wrapping up chapter 6, wrapping up the material for the Unit 1 exam. So a polynomial equation is an equation that contains a polynomial expression. That kind of makes sense. The degree of the equation is the degree of the polynomial. It's the highest power that we see on any of the variables, kind of roughly speaking. And in this course, we're quite interested in second degree polynomial equations. We call these quadratic equations. And recall from previous work, we have the zero product property that if the product of two numbers or two quantities is zero, then either the first is zero or the second is zero or both are zero. So if we have two things that multiply to be zero, at least one of those two things must be zero. So let's take a look at some examples. So if we want to solve this, well, this would be a quadratic equation. If we multiplied this out and combined all of our like terms, we would have a 30x squared plus something times x plus some constant. So the highest power that we see is 2. We see that this would be a second degree polynomial in this equation. It's a quadratic equation. But we also recognize that we have something, maybe we'll call it A, times something else, let's call this B, equals 0. Well, the product of these two things is 0. That means either 5x plus 1 equals 0 or 6x minus 1 equals 0. So now we kind of have two linear equations to solve, and we can solve these one at a time. So over here, I subtract the 1 over and divide by 5. And on the right side, I add 1 to both sides and divide by 6. And then typically I'll write my answer as something like x equals negative 1/5 or x equals 1/6, and say that that is my answer. I have two different numbers that are solutions to this equation. And a lot of times I'll just write something like x equals negative 1/5, comma 1/6, or maybe even just not the x equals when the context is clear. So I might just write like negative 1/5, comma 1/6, or negative 1/5, 1/6 next to each other, something like that. If we look at an example like this, again, we see that we have the product of two things equals 0. So that means either 2x equals 0 or 6x minus 3 equals 0. So again, I end up with two different linear equations in one variable. If I look at the left one, divide both sides by 2, and I just get x equals 0 over 2, or just x equals 0. In fact, if I wanted to, I could just use my zero product property here as well. 2 times x equals 0, either 2 is 0 or x is 0. Well, of course, 2 is not 0, so x must be 0. And then solving the linear equation on the right, 6x equals 3, x equals 3/6, which is 1/2. So we see that x equals 0 or 1/2. So these will be the two solutions to this equation. Typically, kind of the usual case with a quadratic equation is that we get two solutions. So kind of maybe typical or standard or whatever case is that the number of solutions we get is the same as the degree of the polynomial that's in our equation. Now, that's not always true. Uh, we could have a quadratic equation that has one solution or even zero solutions. But the kind of, what we might call like the canonical case is that our number of solutions matches the degree of the equation. Okay, so let's look at this equation. 4x squared plus 7x plus 3 equals 0. If we want to solve this, we might be tempted to do something like try to isolate the variable. That would be a perfectly reasonable thing to think should work. But I kind of see that I have an issue. I have two unlike terms that have the variable in it. And I don't really know how to get from here to something like x equals number. If I try to subtract the 4x squared over to the other side, then I have a variable on both sides, and the same if I try to put the 7x on the other side. So this is a good first thought, but this strategy typically doesn't work in quadratic equations. So what's an alternative strategy? What's my goal here? My goal is actually to use this zero product property. My goal is to take the left-hand side, or the quadratic function, or the quadratic expression, and factor it into the product of two things. And I want that product to be 0. Right? I could have thought of this as the quadratic equation. My first give me 6 times 5 is 30, x squared, and then minus 5x plus 6x would be plus x, and then 1 times negative 1 is minus 1 equals 0. Right, I could have thought of this as, it's really this more complicated looking quadratic equation that I could convert into something like this and then use this solution method. So can I do that here? Well, to accomplish that, I need to factor 4x squared plus 7x plus 3. And it's crucial that I have this equals 0 on the right-hand side. I'm going to really leverage that later on, right? This equals 0 needs to be there so that I can use the zero product property. So everything is on the left side. All my variables and constants and everything are on the same side with an equals 0 on the other side. And now I'll factor. So a times c is 4 times 3, or 12. So I'm looking for m and n such that m times n is 12 and m plus n is 7. And I think that's going to be 4 plus 3. So I need 4x squared plus 4x plus 3x. That's our plus 7x, and then plus 3. And this equals 0. We'll just kind of bring it along. So using the AC grouping method, I'm now going to factor by grouping. Look at my first two terms. I can factor out of 4x times x plus 1. And my last two terms, 3 times x plus 1. And now I can factor an x plus 1 out. And that's what I get. X plus 1 times 4x plus 3 equals 0. And I notice that that looks a lot like this type of equation. And I know how to solve this. I use the zero product property. So I have, say a times b equals 0. Either x plus 1 equals 0 or 4x plus 3 equals 0. So either x equals -1 or x equals -3/4. Any questions so far? All right, let's solve this equation in two different ways. So method 1 is kind of a direct, just a direct equation solving step. If I have some number squared equals 49, well, if I had 2x equals 49, I'd divide by 2. If I have multiplication by 2 on the x, I divide by 2 to get rid of the multiplication by 2. Or if I had x plus 2 equals 49, I'd subtract 2, right? The subtraction of 2 undoes the addition of 2. So if I'm performing some operation to x to isolate x, I kind of perform an operation that undoes that first operation. If I have x squared equals 49, x is getting squared or multiplied by itself, I can take the square root of both sides and get x equals square root of 49, or x equals 7. Now there's something interesting that happened here. I had a quadratic equation, but it kind of naturally seems like I only got one solution. Let's try to solve this a second way and see if we get any clarification. I could, for any quadratic equation, I can force it into this mold, right? I can push everything to the left and get x squared minus 49 equals 0. And then I can say, okay, I want to factor this and use the zero product property. Well, this factors to x minus 7 times x plus 7 equals 0. or x minus 7 equals 0, or x plus 7 equals 0, or in other words, x equals 7, or x equals negative 7. We actually found a second solution. Is x equals negative 7 a solution? Well, yeah, sure, because negative 7 squared is positive 49. The negative sign squares off. We have to be very careful when we're doing this operation, quote, take the square root of both sides. We have to be very careful because doing that kind of in some sense would lose a bit of information. It would lose some information that we have solutions. We have two solutions, one of which is positive and the other of which is negative. So really, I want to say x equals positive or negative 7. So we have to be careful if we ever want to use the idea of just take the square root of both sides of an equation. We have to make sure that we account for the fact that when we have a number squared, that kind of squares off the negative. So I can put in a positive value, square it, and get a certain number as an output. And if I put in the equivalent negative value, if I put in the opposite of that, that also gives me the same output. But if I square root both sides, basically the problem is the idea of the notation square root of 49. This relates to what we call the principal square root, or the positive square root, the positive 7 in this case. So when we use the radical sign, we're indicating the principal square root, the positive square root, and we have to be careful that we don't forget about the negative square root. Be really careful. This notation does not mean plus or minus 7. Right? So little notational bit there. The square root of 49, for instance, is positive 7, and we account for the negative answer by putting a plus or minus in front of it. Okay, and one last problem in this section. This can be kind of a tricky problem to deal with. If I have something like this, x plus 6 times x minus 3 equals negative 8, I'm really tempted to try to use something like a zero product property here to try to say, I don't know, something like, x plus 6 equals negative 8, or x minus 3 equals negative 8, and go from here. But I kind of see that this isn't going to work, right? I mean, if I just try it, this will be x equals negative 5. Negative 5 minus 3 gives me negative 8 here, but negative 5, well, I mistakenly, or no, okay. Negative 5 plus 6 would give me plus 1 here. I mistakenly ended up with the right solution. If I try subtracting 6 over here, I get x equals negative 14. That was a bad coincidence. I just pulled this problem from the book and it was an unlucky coincidence. But if I did x equals negative 14, negative 14 plus 6 is negative 8. Negative 14 minus 3 is negative 17. And clearly negative 8 times negative 17 is not equal to negative 8. So we can't just go and apply a zero product property kind of idea anytime we want, because we don't have a 0 on the right-hand side. In other words, if a times b equals number, we can't say either a is that number or b is that number, right? But we can only say that with 0 on the right-hand side. So what do I want to do here? Well, actually, what I want to do seems quite counterintuitive. What I want to do is take this left-hand side and actually multiply it out. I want to kind of undo the factoring. So I get x squared from my firsts my outside's minus 3x, my inside's plus 6x, so that's plus 3x, minus 3 plus 6. And then my last give me minus 18 equals negative 8. And now I want to set myself up to use the zero product property. I have to add 8 to both sides. Minus 18 plus 8 is minus 10. And now I have a 0 on the right-hand side. And now I want to factor again, but note that the factorization isn't going to look exactly the same as up here. So I'm looking for two numbers that multiply to negative 10 and then add to positive 3. That should be plus 5 and minus 2. We check x squared plus 5x minus 2x is plus 3x. That looks good. And then 5 times negative 2 is negative 10. So I multiplied, I moved the negative 8 to the left side, and then I factored again. It doesn't seem like I accomplished all that much, but what I did was this right-hand side, when I had up here, product of two things equals number. Well, now I have product of two things equals 0. Now I can apply my zero product property. So x plus 5 equals 0, or x minus 2 equals 0. And we have x equals minus 5, or x equals 2. So the kind of general strategy with these quadratic equations, if we have an equation that has a second degree polynomial in it, is we multiply everything out, we expand everything as much as we can. We put all of our constants on one side, then we factor, and we get our solutions, and we typically expect to get two solutions. Sometimes we can get one solution. For instance, if we had ended up with x plus 5 times x plus 5 equals 0, well, then x equals negative 5 would be our only solution. So this, maybe from a different problem, we might get an answer like this. Or we could get an example like, say, x squared plus 1 equals 0, where this left-hand side doesn't factor. Or where we have x squared equals negative 1, and we know that any real number squared is going to be non-negative. It's going to be either 0 or positive. Because if I took a negative number and square it, it gets becomes a positive number, and if I take a positive number and square it, it's a positive number. So we could have no solution. Those are our other two special cases. And we'll actually come back to quadratic equations in another chapter or so. So a little bit later in the course, we'll come back to quadratic equations, and we'll investigate them actually quite a bit more thoroughly. But we need to build up a little bit more information about things like how square roots and other types of radicals work before we really tackle that. So we're going to see some more information on quadratic equations a bit later in the course. But this is the important idea for chapter 6. As we put everything on the left, try to use our zero product property. If we're already set up for it, great. And if we're not, we multiply everything out, we put everything on the left, combine all our like terms, factor, and then use our zero product property. Even if we can get away with avoiding the zero product property, like we maybe could here because there was no linear term, we could get away with not using the zero product property. It's easy to make a mistake if we do that. So still, even in a simpler case like this, I think it's good to follow the same strategy because you won't miss one of your answers that way. If you use the zero product property, it makes it very clear that there are two answers to this problem. If you don't use it, it's super easy to forget that there's this kind of mirror in some sense, or this negative answer, and just write down x equals 7 as the answer and move on. Really easy to make that mistake with method 1. But with method 2, if you ask, how do I factor x squared minus 49, it's really clear that it's going to be two linear factors and you're going to get two distinct answers. So any questions on polynomials and factoring or solving polynomial equations? Okay. So moving on to chapter 7, which deals with rational expressions, and looking at 7.1, multiplying and dividing rational expressions. So what is a rational expression? Well, it's a ratio, which is where the term rational comes from, ratio. It's a ratio of two polynomials. That is, it's an expression of the form p over q, where p and q are polynomials, and where q is not 0. So for instance, something like this, a linear polynomial divided by a linear polynomial, or maybe something like this, a linear over a quadratic. These would be examples of rational expressions. We say that a restricted value of a rational expression is a potential input. It's a real number for which the denominator is 0. So potential input, in other words, a real number for which the denominator is 0. That is where q equals 0 in the above definition. I think your book says something like that they talk about these being undefined. I don't particularly like that because a function naturally comes along with a domain. So I could say, f of x equals 3x plus 1, not in terms of rational expressions, but just in terms of general functions. And, I could impose a restriction x bigger than 0. So technically speaking, this function, along with its domain, is undefined at 0, or it's undefined at -10, because I haven't defined it there. This function has a natural domain that's all real numbers. So in other words, if I didn't explicitly state a restriction of the domain, I would presume that, that the domain under consideration is all real numbers. But that's not always true. We can impose a domain restriction on our function. So, when your book is saying things like we call undefined values or undefined inputs or whatever, we say that's what it is, or that's the set of numbers where q is 0. Well, there are other ways to have inputs where the function is undefined, for instance, just by setting a domain restriction and saying we're only defining it for these numbers. So I think that's a poor use of terminology. So I'm being a little more careful here. I'm using the terminology restricted value to mean something very specific. This is a value where even if we wanted to use it as an input, even if it was in the domain that we're kind of trying to allow, so to speak, well, that's where the denominator is 0, where our rational expression doesn't make sense, right? We can't divide by 0, and these restricted values are real number inputs where we would divide by 0. So these are restricted values in the sense that they're restricted from even being allowed to be part of the domain. There are other numbers that could be allowed to be part of the domain, and we might just choose a domain that doesn't include those numbers. My function will be undefined there because those numbers aren't part of the domain. But I'm kind of like not allowed to use restricted values as part of my domain. So it's not just that the function is undefined there, but it's kind of like we're not allowed to even try to define the function there. Okay. So I like this terminology a little bit more. So let's identify the restricted values in these following three rational expressions. Again, for restricted values, we're only looking at the denominator. Right? We only have a potential problem with the domain when the denominator is 0. So restricted values for this rational expression will be when 2x equals 0 or when x equals 0. And if there's no domain restriction placed yet, if we're just talking about a natural domain, we might write next to this, say something like x not equals 0, or we might write something like the domain is all real numbers except 0. So we might denote it one of those two ways. Or for this one, if we're searching for restricted values, we're asking when is 4x minus 9 equals 0? Or that's whenever x is 9/4. So I might say something like domain is all real numbers take away 9/4, all real numbers except 9/4. Or I might say simply just x not equal to 9/4. Or in this third example, I have a denominator. Well, that's a quadratic function. X squared minus 3x minus 28. And I want to know when is that 0. So I'm looking to identify my restricted values here. And to factor this, I know that I'm looking to solve this quadratic equation, this polynomial equation. I want to factor the left-hand side. I've already got a 0 on the right-hand side. So looking to factor the left-hand side and use my zero product property, looking for two numbers that multiply to negative 28. So they've got to be opposite signs. And that add to negative 3. So the bigger one has to be negative. And I think this is going to be negative 7 and positive 4. Okay, negative 7 times positive 4 gives me negative 28. Negative 7 plus 4 gives me negative 3. That looks good. So x minus 7 times x plus 4 equals 0. And that says that x equals 7 or negative 4. These are my restricted values. So over here next to my function, I might say something like x cannot be 7 or negative 4. Just noting the restrictions on the domain. So the natural domain for this function would be all real numbers except 7 or negative 4. Any other real number I don't have a problem with plugging in. Okay, so we see rational expressions are basically fractions. And we might want to simplify them. We might have a complicated rational expression like, say, this one here. Well, maybe I could write it a little more simply. Maybe I could write an equivalent rational expression, one that for each input in its domain has the same output, but that is simpler to work with. And for this, we're going to use our equivalent fractions property. We have that a over b equals a times c over b times c, of course, so long as b and c are not 0. So for instance, if I wanted to, let me zoom in a little bit so these fractions are a little easier to see on your screen. If I wanted to simplify 12x minus 240 divided by 5x minus 100, Well, what I might do here is I might start searching for common factors between the numerator and denominator. In other words, I might take the numerator, completely factor it, do the same for the denominator, and look for factors that divide out. So 12x minus 240, I can factor out a 12, and that is x minus 20. Divided by, and 5x minus 100, I can factor out a 5 times x minus 20. And I actually see that I have a factor of x minus 20 in both the numerator and the denominator. So that's 12/5. So I might be tempted to write something like 12x minus 240 over 5x minus 100 equals 12/5 and just kind of leave it there and move on. This is really, really close to being right. There's one little nuance though. On the right-hand side, if I look at, say, a function g of x equals 12/5, saying for whatever input, I just give an output of 12/5, this natural domain is all real numbers. But if I look at this rational expression on the left here, let's call this f of x, its natural domain is all real numbers except 20. Because if I try to plug in 20, I get 5 times 20 is 100 minus 100 on the bottom, I get 0 in the denominator. So the left side has a natural domain restriction, x cannot be 20, but the right side, just g of x equals 12/5, does not naturally have that domain restriction. Because I've lost the implication of that domain restriction when I got rid of that x minus 20 on the bottom, I have to explicitly state it. So this might seem like a little nuance, but it is actually quite important. These two sides are not the same thing when I try to evaluate them for x equals 20. The left-hand side would be undefined, or perhaps a better word here is indeterminate, but that's a higher level concept. But the left-hand side would be something like undefined, and the right-hand side would be perfectly well defined. It would be 12/5. So we have to exclude the potential input 20 because we would have a discrepancy there. But for any other input, any other potential input, 21 or negative 100 or whatever, we would have the same output on both sides of the equation. So it's just kind of good practice to just explicitly write our restricted values, and then that's kind of taken care of. We just don't have to deal with that. We just say, don't allow x to be 20 from this point forward. It's over and done with, and now we can proceed and do our algebraic simplifications, and everything is good. Okay, so let me take a look at this rational expression. Let's try to simplify it. The first thing that I'll do, I don't really worry about restricted values right away, because to simplify, I have to factor my denominator anyway, and to find restricted values, I probably have to factor my denominator, so I'll just start by factoring everything. Just factoring things doesn't really change anything about restricted values. So let me factor the denominator. I think that's going to be a -5 and a -1 for our m and n. -5 and -1 multiply to make +5 and add to make -6. Looks good. And for my numerator, I need what? I need two numbers that multiply to make -4. So they need to be opposite signs, and add to be +3. So I think that's +4 minus 1. Now that I've got everything factored, I can do two things really quickly. I can find my restricted values. Y not equal to 5 or 1. So at no point in this string of equalities am I allowed to use inputs of 5 or 1. And the other thing that I can do is I can divide out this common factor of y minus 1. These two pieces together yield the answer. We see that there's still the implied domain restriction, y not equal 5. We still see that y minus 5 in the denominator. But because we divided out the y minus 1, we don't see an implication in this more simplified version. We don't see the implication of y not equals 1. But that is a domain restriction from the original rational expression. So we want to make sure to find our restricted values and note those, and then do our simplification. And then those two pieces combined give the answer. So the simplified version of this rational expression is y plus 4 over y minus 5, where y is not equal to 5 or 1. Again, y not equal to 5 is still implied in this simplified form, but y not equal to 1, we lost the implication of that. We lost the apparent fact that y cannot be 1. And what about a rational expression like this? Looks very messy. In fact, this has two variables that are involved, r and s. I'm not really sure where to even almost start here. Well, let's start by factoring. Can I factor the denominator? Well, I recognize this is a difference of two squares. This is r squared minus 7s squared. So I think this is r minus 7s times r plus 7s. My numerator, those are pretty big numbers, but nicely enough, I recognize I have a common factor of 5 everywhere. And then 5 goes into 245. How many times? Well, 5 goes into 120 times, so into 240 times. And then I have 45 more, which is 9 times 5. So I think this is 29. 49, geez. 20, and then 20, and then 9. And I see this has the potential to be a perfect square trinomial. And I do note that that cross term does match with the perfect square pattern. My a would be r for a squared, and my b, I want b squared as the other squared term, so b would be 7s, and then 2ab would be 2 times r times 7s. So I have a equals r, b equals 7s. So I think I have r plus, because I have a plus there, 7s squared. What is my domain restriction here? It's a little bit more complicated. I really wouldn't fault you if you didn't write it down, because this is kind of more complicated than the previous ones, but we see that r cannot be equal to 7s, and r cannot be equal to negative 7s. These are kind of our restricted values. They're a little more complicated than our previous ones. Right? When is r minus 7s equals 0? Well, that's when r equals 7s. When is r plus 7s equals 0? Well, that's when r equals negative 7s. That should be a r cannot be equal to. So the denominator is 0 anytime that I choose a value for r that's plus or minus 7 times the value that I chose for s. So in this case, it's not just like a number or two numbers, it's a dependency between the two variables. So a little bit more complicated than before. I found my restricted values. I can also divide out one of my factors of r plus 7s leaving me with r plus 7s over r minus 7s for my simplified form. Right, even a pretty complicated, and I forgot a factor of 5. Even a pretty complicated problem like this one, we follow the same strategy and we get the answer pretty easily. As long as I don't forget to write something down from one step to the next. As kind of a side note, when you're the more complicated the thing you're doing, the more you're focused on the complicated stuff, like making sure that I do all the factoring and the squares and all that correctly. And kind of the easier it is to let some of the simpler stuff slip by, like just forgetting to copy up this factor of 5, right? Just a flat out copying error. Um, Things like that, or things like dropping a negative sign. Super easy when you have a lot of complicated stuff going on, when there's a lot of steps involved. So um, it's always good at the end to just take a glance back and kind of see if everything seems reasonable. And I took a glance back and noticed that originally I had this 5 here and I somehow lost that and couldn't figure out how I lost it. It's like, oh yeah, okay, I just forgot to copy it. So a good habit to get into is kind of performing those kind of reasonability checks. Take a glance back at your original, in this case, before we simplified anything, and ask, does the simpler form kind of seem to mesh with that? And the answer was no. And why is that? Well, I forgot to copy down the 5. So I go back, I copy it back down, I fix that, right? So especially on problems like this, where there's just a lot of moving parts, a lot going on, double check and make sure that, at the end, that your answer makes sense with the original problem statement, and that, that helps to avoid silly mistakes like this. Not all the time, but, even if you can catch half of these silly mistakes, like that's a big difference in, say, an exam grade or something like that, or a big difference in the amount of hassle and frustration on the homework problem, or a homework set, where if you have 4 homework problems that you're like pulling your hair out over, versus if you only have 2 of those because you're being a little bit more careful and catching some more of those errors, that's a big time save and a big frustration save. And we could look at performing operations on rational expressions. I could have 2 rational expressions, say, multiplied together. If I wanted to multiply and simplify these, what would I do? Well, probably the first thing that I want to do is perform the multiplication. I know that I'm eventually looking forward and I'm saying, okay, I think that I'm probably going to want to factor everything. So I don't want to distribute. I don't want to kind of unfactor at this point. I'll keep it factored, or slightly factored, I suppose. Now I have a single rational expression, polynomial over polynomial. I'll factor the rest of the way. X squared minus 16 factors into x minus 4 times x plus 4. X squared minus 5x minus 36. I think that m and n are -9 and +4. And I have everything factored down to linear factors now. Now I do 2 things. I find my restricted values before I start canceling stuff. I can't allow x minus 9 to be 0, or I can't allow x to be 9. I can't allow x plus 4 to be 0, or x is not -4. And I also cannot allow 10 times x to be 0, or x cannot be 0. These are my restricted values. And now I can divide out some common factors. The x plus 4s divide out. I see a factor of 5 divides between the top and bottom, leaving me with a factor of 2. And a factor of x divides from the top. I lose one of my powers of x squared, x times x. One of the x's goes away, divides out with the bottom. Or I'm left with x times x minus 4 divided by x minus 9 times 2. Now, what's a more simple form? Is this a simpler form than if I multiplied out the top and bottom? I don't know. That's a matter of taste, or maybe a matter of what you want to do with it next. I'd probably just leave it like this. But it wouldn't be wrong to multiply it out and make it x squared minus 4x over 2x minus 18. I don't think that would be wrong either. I think it's a matter of taste or a question of what you plan to do with it next. We still do see the implied domain restriction that x can't be 9, but we lost the implied domain restriction x cannot be -4 and x cannot be 0. That's why it's important for us to explicitly list our restricted values before going and dividing everything out, so we know what those domain restrictions are. This original product had these domain restrictions of 9, -4, and 0. We need to respect that in the end result as well. If we try to plug in, say, 0 into our boxed answer here, it would look like that's a perfectly fine thing to do. We just get an output of 0. But if we try to plug in 0 up here, it's roughly speaking undefined. Okay. So we need to make sure to list our domain restrictions alongside our simplified form. Then let's do one more in the last few minutes we have left, and maybe we'll leave division to next time. Division works pretty much the same way as up here, but there's one little nuance that we have to be careful about with the restricted values. Okay, so I have 7y minus 12y squared, or that's y times 7 minus 12y, multiplied by y squared plus 10y plus 24. That should be y plus 6 times y plus 4. 6 and 4 multiply to make 24 and add to make 10. 8y plus 32, I think that should be 8 times y plus 4 multiplied by y squared minus 36, difference of two squares, y plus 6, y minus 6. I see that I have restricted values, that x cannot be -4 or 6 or -6. That comes from the factors of y plus 4, y plus 6, and y minus 6 in the denominator. And I can now divide out common factors. The y plus 6's divide out. These y plus 4's divide out. And I have y times 7 minus 12y over 8 times y minus 6. And again, this simplified form, along with, very importantly, the restricted values, we lost the implication of, I wrote x here, that should be y. We lost the implication of -4 and -6 being domain restrictions. So it is important to list these restricted values explicitly before we start dividing things out and getting a simplified form. But these two pieces together, these two boxes together, would be our simplified form. And like I said, when we come back, we'll talk about division. We do have to be a little careful here because not only do we have restricted values where either of our component rational expressions has a denominator of 0, but we also can't allow this second rational expression we're dividing by to have an output of 0. In other words, we can't allow the numerator of the divisor to be 0 either, because then we'd have something divided by 0 where this whole thing would be 0. So we'll have one extra little check to make for our restricted values. So that's the nuance with that one. Okay, that wraps us up for today. I will end the recording.